Now we are going to look at another example of linear first order. And this will actually have a initial condition. So here we first find the general solution, then we use the initial condition to find the specific solution. Exactly the way we did separable differential equation. Here, if you look at, you should actually pause, and you might want to pause and try to do this yourself. But let's actually do it now. So it is not in the standard form because the coefficient of y prime is not 1, is actually t. So you have to divide both sides by t. So let's divide both sides by t. So I'm dividing both sides by t. And of course, t square over t is t, minus t divided by t is 1, plus 1 divided by t. So I'm dividing all of this term by t. Now this is in the standard form. So here, the p is 2 over t. Uh, Again, if I have a sign on the left, right, that's part of p. So if I happen to have a negative sign there, my p is going to be negative 2 over 2, negative 2 over t. So you have to include the sign on the left. That is very important to remember. And the q is this, the right hand side. That's my q. So let's go through the procedure. The step one, you find the integrating factor u, which is e to the power integral of p dt. I can bring my 2 outside the integral. And then the integral of 1 over t is ln of t. Should put an absolute value there. Okay. And then remember your plus c is 0 for the integrating factor. You do not add any c. The 2, I can put it on the exponent. So let's do that. So if I put it on the exponent, I get absolute value of t square. Okay. And then I can just simply write this as t square. Okay. And again, I don't have to put the absolute value of t here because t is bigger than 0. They only want t is bigger than 0, but I did that anyway. Okay. Here I want to remind you that e and ln are exponential function. So this means that, for example, e to the ln of something is equal to that something. It's like e and ln cancel each other. They are inverse function. Just like sine and sine inverse cancel each other, they are inverse function. Okay. So that is what I did here. So this e to the ln of t square is t square. I can forget the absolute value because t square is positive anyway, and in the question they say t is bigger than 0. So I forget the absolute value. So finally, my u is just t square. You do have to make that simplification, otherwise your algebra will be quite complicated. Now let's find the y. So my y is equal to, remember the formula, something over something. On the top is integral of u times q dt. Here t is the variable, divided by u. My u is t square, so t square goes in place of u. How about q? Q is here, right? So that is my q, so that goes in place of q. Let's do that. The integral of u times q, let's put our q there. Maybe I can zoom out a little bit so I can. So my q is t minus 1 plus 1 over t. So that's my q, this one, divided by u is t square. Okay. Let's evaluate this integral. It's a calculus 1 integral, which we can all do it. So let's do that. Let me first multiply out the t square. Let's evaluate the integral on the top. So the integral of t cube is 1 over 4 t to the power 4 minus the integral of t square is 1 over 3 t to the power 3 plus the integral of t is 1 over 2 t square plus c. At this point, you have to have that plus c divided by t square. If you want, you can distribute this t square under each term. So let's actually do that. If I distribute t square, I'll get y equal to 1 over 4 t square minus 1 over 3 t plus 1 over 2 plus c over t square, which is c. Okay, let me write c over t square. If you want, you can write c t to the power negative 2. And that's my general solution. That's a general explicit solution. But we're not done because we have the initial condition, right? So let's look at the initial condition. My initial condition is y of 1 equal to half. So my initial condition is y of 1 equal to half. So this means when t is equal to 1, y is equal to half. If you think about the point, so this is my point 1 comma half. Okay, so my graph has to go through this point 1 comma half. So the way we did the separable differential equation, we can use the geometry to approximate the value of c, but let's actually use the algebra to find the c. So I'm going to replace y by half and t by 1 on our general solution. So I'm going to replace the y by half equal to, and I'm going to replace t by 1. So in the previous general solution that you see on the top from here, I'm replacing y by half and t by 1. Like that. Okay, and then this will give you the value of c. Let's find out what is my c. Okay, I can subtract 1 half from both sides, so that's gone. Okay, so my c is going to be equal to 1/3 minus 1 over 4. So you're going to move it to the other side, right? So negative 1/3 become positive 1/3, and positive 1/4 become negative 1/4, right? And then here you combine this fraction, right? You make the denominator same. So that will be 4 minus 3 over 12, or 1 over 12. So my c is 1 over 12. Okay, and then you go, and then we're going to replace my c by 1 over 12. So here I need to replace my c by 1 over 12, and that will be my specific solution. So I'll copy everything except I'm going to replace c by 1 over 12. So let's do that. Let me actually copy this down so you can clearly see here. So okay, I'm going to, so my specific solution, after we solve the initial condition, the specific solution. Okay, so this will be the specific solution is y equal to 1 over 4 t square minus 1/3 t plus 1 half plus I'm going to replace c by 1 over, so this 1 over 12 is goes in place of c. So let's do that. So I get 1 over 12 divided by t square. But instead of writing like that, I can just simply put the 12 in the denominator, right? So 1 over 12 divided by t square is simply 1 over 12 t square. Okay, it looks better. That's it. That is what we get, right? Here, if you ask what is the long-term behavior of this function, so what happened as limit t approaches infinity of this function y, right? What happened to that? You can see that this part, as t approaches infinity, that actually goes to 0, right? So the function is actually approaches this quadratic function. So the long-term behavior of my y is actually a quadratic function. It behaves like a quadratic function. So that's the long-term behavior. So let's look at the GeoGebra and see we can make sense out of it. So so let's actually graph this solution, and also actually let's actually graph the general solution. Let's actually graph the general solution, right? This one, uh, and see what is the picture looks like. So that might be helpful. So let's do that. So I am going to do it here. Oh, this is the previous example, don't worry. Okay, so let's see. I press C and the enter. There's a slider. I explained that before all the videos. So let's write our general solution. So general solution is 1 over 4 t square minus 1 over 3 130 plus, I forgot, let me actually go and check. uh, 1 over 4 t square minus 130 plus 1 half plus c over t square plus 1 half plus 1 half plus c over t square. That's my solution. Is actually have branches, right? Because of this, because of the c over t square, you're going to end up with branches. Very good. And you can see we're only interested when t is bigger than 0, right? So where you can ignore the left part, we're only interested on the right part because my t is bigger than 0. Okay, so it's not really a quadratic equation, right? It's a slanted, because there is some there is a, at this point my c is 1, right? So we have this 1 over t square, so this contribute to this quadratic part. But let's actually move around, right? Wow, what happened when c is negative? Okay, so it's actually the behavior completely changed, right? The behavior completely changed. Okay, so so when c is 0, when c is 0, if I choose c to be 0, right? When c is 0, you see that I have only the quadratic part, right? When c is 0, c over t square vanish, so I have a quadratic part. So they're connected to one graph, right? So in this case, you can say that c equal to 0 is actually a critical value. When c is bigger than 0, we have some behavior of this graph, and when c is less than 0, it's a kind of a different behavior of this graph, right? So when c is bigger than 0, it's like a two branch, right? You have two branch. If you look at the whole thing, not just t is bigger than 0, you have this, two branches of this solution. And here the function decrease and then increase, and then in this part again decrease and then increase, right? When c is less than 0, right, it seems like the function is always decreasing, right? The both branch, the function is always decreasing. You don't have any minimum or maximum like that. It's always decreasing. So it's a completely different types of behavior. So c equal to 0 distinguish between these two behavior. It's like a borderline. So my c equal to 0 is the borderline. When c is bigger than 0 is a one type of behavior. When c is less than 0 is another type of behavior. So in that sense, c equal to 0 is like a critical value, is an important value. Okay, now here let's substitute our initial condition. Our initial condition, if you remember, my t is equal to 1 and y is actually half. So if you look at this as a point, that's my point. And for what value of c the function is actually touch or goes through that point A, right? We actually know. So if you look at our solution for the initial condition, right, my c is supposed to be 1 over 12 when that happened, right? 1 over 12, if let's actually make it a decimal, right? 1 divided by 12. So that is like 0.0833, right? Okay, so let's look at here. So let's look at our here, right? So let's actually slide and see when that happened, right? So when I slide, I see, oh, what happened here? Why I cannot slide? Okay, so let's slide. Okay, so when I slide right there, oh, right there. Okay, you can see. Let's actually here. Okay, so it's looked like C 0.1. So and, it's it's not really on the top. You can see that, right? So maybe I have to decrease a little bit. It's very difficult. It's very difficult. So it's not going to be accurate. It's not going to be accurate. Okay, it's not going to be accurate. But let's actually put our value, this 0.08. Let's actually put it here, 0.08, and that's actually that's actually on. It goes through this point A. Again, a geometric way is not and 100% accurate, right? So by algebra, we know is approximately 0.08. It's actually 0.083333. So you get the idea. So this one is our specific solution. And you can see that in the long run, this function is approaching this quadratic part, right? If I just graph that quadratic part, 1 over 4. So let me actually just graph this quadratic part. So I'm just going to copy this here, this part. uh, Let me actually copy here. Sorry, can we copy that? Control C, Control V, and I'm just going to forget that part here. Okay, so let me change the color. Okay, very good. Okay, I uh, so the original function is gone. Actually, let me go back. Okay, yes. uh, Let me actually, let's try one more time. Let's call it g of t, and then I'm going to forget that part over here. Okay, now you can see, right? So this purple one, that's my quadratic function. And you can see this blue one, our blue one, right? This specific solution when c is 1 over 12. So that's the blue one, right? Let's concentrate on that. And that solution is actually approaching that quadratic function as t approaches infinity, right? They're getting close and close and close. In the if you go to the when t is like uh, 5.8, even when t is 6, right? You don't really see a big difference here. Okay? You don't really see a big difference. They're top of each other. Always remember, you can do it. Yes, you can do it. Bye bye.